Oh, hi. Sorry, I was in the forums. I guess it's time for this week's video. So this week we're moving from history to technology, and in a sense we're going to tell the same story again. We'll sort of start at the beginning, but we're going to start from the bottom and work upwards. So since we're kind of talking about the same things, but just from a more technical perspective. Don't worry, you'll be fine. We're not going to there's no math, I promise. There's no programming. Don't worry about that. So, of course, I appreciate IEEE Computer Magazine, who I write for, to let me use the articles that are associated with some of the videos, as well as the folks from Open Michigan who have helped me. So, hang on a sec. No, hang on. Got a phone call. I'll be right back. Okay, well, that's been sent. Sorry for that interruption. Again, I thank everybody for the use of the copyright materials. Part of my hidden agenda in this class is that you will be able to look at this XKCD comic and you'll understand the humor. So I'm going to stop for a moment and let you look at it and see if you get the humor. Okay, so maybe you did, maybe you didn't, but hopefully by the time we're done, you'll have a better chance of getting the humor. So if you recall, the most academics throughout the 60s, 70s, and 80s, the best they had access to was this store and forward networking, where you would send a message and it would go into a computer and it might sit for some time, then it would find its way across a network and it would sit for a little while longer, find it and hop. And there's these multiple hops. We call these hops. And each of these would be a couple hundred miles perhaps. And to go from, say, Michigan to Stanford, there might be 15 or 20 hops. The hops are as much defined by geography, where we're all trying to optimize the cost of these long-distance connections. So the thing that really characterized store and forward networking was that there wasn't a lot of sharing. One message was being sent across one of these links at a time, and all the other messages just kind of waited in line. Now, that the innovation that happened in the research networks in the 60s through the 80s, ultimately embodied in the ARPANET, was the fact that they were going to be packet networks. First, how do we share one link so that a long message doesn't clog it up? And how do we deal with outages more dynamically? With the idea that eventually you could send a packet across the country and back into a computer and back out in maybe a half of a second. And that was seen as something to do rather than somewhere between 10 minutes and a day or two. So how to do this efficiently? It was a research project, and it was a research project that lasted almost 20 years, and 20 or more years. And one of the neatest things about this is they were able to throw it away and rewrite it a bunch of times so that they could put something in production, see its flaws, see what was good about it, then they had the money from DARPA to throw it away and rewrite it. Now, by the late 1970s, it had, 100-ish computers on it. Here's a picture. And these are not the schools, these are the computers. These are, listing all of the computers that are there. And so the engine, the innovation that they spent 20 years perfecting was the notion of packet switching. So how can we simply move data simultaneously across a connection? And the essential brilliant idea is break the message into packets. And again, to sort of review, here I have a message and I have postcards that only can handle 10 characters, and I'm going to send this "Hello there, have a nice day" message to Daphne in California. And so I have 3 10-character postcards. I basically put a from address and a to address on each postcard and a sequence number on each postcard, 1, 2, and 3, and I put 10 characters on each. And then I stick them in my mailbox. I just put them in, put the sign up, and then I wait. Now, let's just say, that the post office person comes and picks this first one up, and it goes to Chicago from Michigan, and then it goes to Omaha, goes to Denver, and then the second one kind of falls on the floor, and it ends up going to Charlotte, North Carolina. And then they're like, why is this here? And then they send it to Atlanta to get checked, and then they make sure, and this one goes, and and number 3 ends up going to St. Louis, and then Tulsa, and then Colorado, and this one gets routed back to Charlotte because they weren't sure why they sent it to them in the first place, and then they sent it to Memphis, Tennessee, and then this one makes it to California, and then this other one sort of goes to Phoenix, and this one finally gets to Dallas, Texas, and this other one goes finally, and then this third one goes to Tucson, Arizona, and then Las Vegas, Nevada, and finally it makes it, right? So these poor little postcards that I put in, they have each a different journey, right? It's a little adventure for each of the postcards that they go through. And so I don't see how this works on my end. I put in 3 postcards. I numbered them 1, 2, 3. But on the far end in California, Daphne opens her mailbox and has scribbling all over her mailbox. Oh, the shame. No, actually, we'll get rid of the scribbling. So Daphne opens up her mailbox, and she doesn't know how these packets got there. I read postcards, how they got there. Out comes the first one. She goes, oh, it looks like I got a message from Chuck, but I've only got part of it. Then out comes the second one shortly thereafter. And then after a long period of time, finally the third one comes out, but it's actually the second one. And now she understands that she's got the entire message, and she reassembles it, and away we go. And so this is the basic notion of how all those postcards can share the infrastructure. They can all be in flight at the same time. They can take different paths. You don't have to connect them all together like trains, basically. And this led to a shared network infrastructure. And so the computers that were in a store and forward network went from sort of big, powerful computers with disk drives to really tiny computers with a single purpose of forwarding packets rather than long-term storage of message. And so the store and forward had long-term storage of messages in the routers. But I mean not in the routers. In the store and forward, the old one, long-term storage was somewhere in the network. But this was only short-term, right? Short-term storage. And so when a packet comes out, it simply has to find its way through a series of hops. It still hops, and it's still connections, but basically it has to find its way across the internet. And then we would take whole campuses, like University of Michigan, say, or Stanford, for example, and then we'd have sort of various kinds of local networks on those campuses and computers on the campuses and servers and various things, and they would route all their packets, all their data out to the internet, and then the packets would find their way across the internet, and then we might have a home connection as well that might connect. And so the shared network infrastructure focuses only on packets, not reliability or anything else. So this notion of hops didn't go away. As a matter of fact, I don't know how many hops it took to get from Ann Arbor to Palo Alto in using BitNet. I'm going to guess it might have been 16 or 20, and these days it takes 16 or 20 hops. The difference is in the internet, the 16 or 20 hops happens in 1/100 of a second or 1/10 of a second. So the notion of hops and the notion of intermediate computers is still present in the internet and the TCP/IP networks that we use today. And so your message sort of leaves you the host that you're in, hops to the first router, and then hops to however many routers, ... This is more of a ... thing, and then finally hops its way out to the far host. And so this is sort of either your computer, maybe Stanford's web server, and then there's this series of routers in the middle that it hops through. Okay? And so the problem of what data goes between here and here is you got to solve a lot of problems, right? All kinds of problems. And so in order to simplify the solution or break the solution into simpler, more manageable parts, they came up with a layered network model. Now, this is a cartoon, and computer people love drawing cartoons and saying this is our architecture, this is our framework, this is our approach. Sometimes they're helpful, sometimes they're not helpful. Sometimes the cartoon is just kind of a cartoon. But what's usually being communicated in these kinds of pictures is they're taking a big problem and breaking it down into some subset, some set of smaller problems. So the whole problem that they've got to solve of getting data reliably across the whole country is that big. And if we can break it into 4 pieces and work separately and come up with ways to let these pieces interact, work separately with each one, then maybe we'll have a better solution. Okay? So take a problem that's so large and so complex that we might not be able to solve it and break it into 4 smaller problems gives us a better chance of solving the 4 problems. Now, there's a certain art to picking how you break the problem up. And there's more than one network model. The one that we use in the internet is the TCP/IP or Internet Protocol Suite model, and we'll meet some of the people who designed that. There was also a model called the 7-layer OSI model, Open System Interconnection model. So there's a model out there that has 1, 2, 3, 4, 5, 6, 7 layers, and they all have names, and they all have purposes, and they all have definitions. This was not This was not very popular, and I doubt that it's many places, because the TCP/I model is the one that kind of won, and so that's the one that we're going to study. But that doesn't mean that that has to be the only one, but it is the one that has become popular on the internet. So once you break the problem down from a big problem into 4 small problems, you have to develop documents about how these layers work together, how various computers work together, how routers work, all these things. And so early in the process of the development of the ARPANET, they created an open process to build these specifications, where they would invite engineers from all kinds of companies and universities and who knows what, any expertise, to show up at a meeting several times a year. I mentioned the IETF meeting when I was talking about the history of the internet and the Tim Berners-Lee BOF that only 15 people showed up to. That's this meeting. It's the Internet Engineering Task Force, which is just a bunch of engineers that get in many rooms and solve a bunch of problems. And so the standards that come out of this, and you can go read them, they're all open documents. They're very throwback documents. They've got this text thing, and it's got all this like beautiful uppercase that reminds me of back when printers didn't have lowercase. And these are documents that describe how most of the components of the internet work together. So, the layered architecture that I just described, where you have a computer, and then it sends data out the back of it, and then hop, 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 hop through routers, and then the data arrives at the destination computer, and then the destination sends it back, and it's hop, 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 coming back, and it comes to you. We're going to expand on this a little bit. So each of these hosts on the 2 ends is going to expand to this much right here. So that's one host. That's another host. And each of these routers is going to expand into this. So this bottom picture is just an expanded version of this upper picture, so that we can see how the internet layers work together. So when you send a message in on your computer, this is all software, application, transport, internet, link. So this is all software, and then it comes out the little plug on the back of your computer, right? So maybe your computer has a little plug like this on the back of it, right? That's an Ethernet plug, and here's an Ethernet wire, and I plug my local area network in, right? And so this right here is that right there. That's kind of the plug. It might be Wi-Fi, which means it's kind of like air, but if you have a wire like this, then it's a little more tangible. And there's something on the other end of that wire. This is a very short wire, but there would be a router on the other end of that wire. The router takes the data off the wire and then forwards it, just like a post office, intermediate post office would do, onto the next link. Onto the next link. And this would be multiple hops in here. They're only showing 2 hops. And then finally, it's on the last link going to that computer at Stanford. And then it goes up through these 4 layers of software and then goes and does whatever it's going to do. Now when they send you the response back, it kind of goes the other way. Chop, hop, 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 and back up and back to you. So if this was you in a web browser, you know, and then here's me, and here's a slide I've got, right? This web browser, and you moving your cursor in the web browser, is sending stuff back and forth to the Coursera servers, kind of here, and that's what's happening, right? So as we look at this picture over here, this left column is the host you're coming from, the right column is the host you're going to, and the routers are these things in the middle. Okay? Okay. So let's start looking at all 4 layers. We are going to start at the bottom, at the link layer, and then we're going to move up. So if you recall, when I talked about the basic reason why we even have a layered architecture at all, is to simplify the problem. To simplify the problem. So the idea of the link layer is it only worries about getting the data across one hop, right? It only worries about getting the data from across one piece of wire. What like voltage goes on these little wires, and how we send the stuff, and if more than one computer is using the same wire, how do we share? And it's a complex enough problem, but we don't worry about the whole world. We worry about this one link layer. And so the link layer is sort of like the connection out of one computer and into another computer. And this might be fiber optic, might be 40 miles, or it might be 40 feet for all we know. But it's one link, okay? And then a router pulls it off that link and then forwards it onto another link. If you go to the post office, you could think of the person who picks your mail up from your house with the thing on their shoulder. That's one link. Then they put it in a truck, which takes it to a place that puts it in a semi-truck, and then they puts it to another place that puts it on a train, and the semi-truck and the train and the postman or postwoman are these little link layers. Each person or semi-truck is not taking it all the way, they're just getting a little farther. So that's the link layer. So the link layer doesn't worry about the rest of this stuff. The stuff that is defined on this wire really doesn't even care if there's a World Wide Web or anything. Its job is to get data across 1 foot. That's what its job is. Is it up? Is it down? How do we share? It doesn't care. It's got a very narrow view. So what it means is we can zoom in on this problem, right? We can zoom in and focus and ignore everything else. So the link layer basically asks questions like, I've got some data inside the computer and I want to send it out. How do I encapsulate it? What if this is shared? How do I deal with that? And common link technologies that we see are like Ethernet or Wi-Fi or cable modem, DSL, satellite, or optical. Right? These are all links layers of one form or another. So if you're going back to this Ethernet link layer, which is one of our favorites because it's kind of ubiquitous, other than wireless, it's probably Ethernet is the most ubiquitous link layer. So when the manufacturer builds an Ethernet or a wireless adapter, they actually build into it, which is probably right here. I don't know, it could be right here. They build into it a serial number. So they mark this as having a serial number. And you can actually, whether you're on Windows or Mac, you can work your way down to find the serial number for your actual manufactured piece of equipment. So there's one on the Mac, that's an example one on the Mac, and that's an example one on the PC. They tend to be 6 2-digit numbers concatenated together, often with colons, or in this case in Windows it shows dashes. And so this is a Raspberry Pi, and all the Raspberry Pis are going to actually have similar prefixes and then serial numbers within that prefix. And so the Raspberry Pis get manufactured. They come out of the manufacturing line with this sequence number just kind of going chug, 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 up, 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 up. And then they get shipped to all corners of the world. And so these numbers are not the numbers for this to get across the world. All these serial numbers at the link layer are good for is to get across one connection in case that connection is shared. And if you were to plug this into a hub and you're plugging other computers into that same hub, well then you're sharing that connection. And this computer might see the traffic for that other computer. And so we use the physical addresses so that this computer knows which of the packets belong to it on the piece of wire. So wired Ethernet or Wi-Fi, certainly if you're sitting in a room with a bunch of Wi-Fi computers, you're sharing the air. So you have to come up with rules how to share this, how to share nicely, and how to behave. So the way it works is and this Ethernet could easily have a bunch of other computers hooked to it, right? Because it's really shared, and so they're all sitting here, they're all talking simultaneously, But we have a pair of computers that want to talk, so it's not just one. It's got a bunch of folks sitting here. Just draw a bunch of them, bunches of folks. They're all talking, or all potentially talking, and we got to figure out how in the shared medium, like think of this as a hub, and they're all connected into this hub. including the two we want to talk. They're all connected in the hub, including the two that we want to talk. And how can these two make sure that the data goes, is this data that's sent with the intention of going to this computer, this router, how can it make sure that it gets there? Well, if it knows the address of the sending and receiving unit, it just encodes that in the packet. And that way it sort of goes by all these folks. Let me change colors here. The packet we send goes by all these folks, and even if they all heard every one of the packets, they all know that it doesn't belong to them because they all have a different number, and this is the only one that responds to it. So that allows them to share the wireless or the wire and share the wireless or the wire and have it all work out for them. So that's the idea of the link layer. Now again, remember, this might only be 50 feet or 50 yards or 50 meters. We'll make it meters. It's only 50 meters, but you still have to share the network in that 50 meters. And then the router takes it off of that and forwards it on a different link. And that's how we get across the country. But that's the next layer up, and let's not worry about that for now. So the idea is, think about one link, whether it's fiber optic or cable or wireless or Wi-Fi. And so what are the kind of problems that you have to solve on this link layer? Well, so one of the things that's cool about many link layers is, like wireless and Ethernet, is they can be shared. And it makes it really easy to just plug new computers in. So you just sort of like, here's a hub and you just plug another computer in and it's on the network. But they have to come up with a way to avoid the chaos when they're sharing. And so the way Ethernet does this is with a technique called carrier sense media access with collision detection. And as you'll see, a lot of the things that we do on the internet have a lot to do with courtesy, meaning that we're just nice. And if everybody's nice, it all works out. It's kind of like driving in a car. Everyone can't run through the stop sign at the same time. Somebody's got to stop, got a green light, your turn, my turn, whatever. This probably wouldn't work so well with cars because sometimes you do have a collision of packets. You just have to wait. Packet collisions don't crush your car. They just slow your data down. So here we go. This is basically carrier sense media access with collision detection. The first thing you do if you want to send some data, say we got some data inside a little computer and we want to send it out, knowing that there might be other data going by, the first thing we do is we listen. We listen to what's on there. If it's not silent, we just wait until it goes silent, and then we start sending. So if someone's already using it, why crash into their data and crush their data? Because it's shared. There's only one. You can't both be sending at the same time. So first you listen. Once it's silent, you begin transmitting data. And then what you do is you also listen to your own data. And if your own data is coming back, then it's sounding pretty good. And then if there is a collision, because there's a chance that two computers will want to send at the same time and they'll collide, then what they have to do is back off. And they have a sophisticated random number calculation so that they back off not always the same amount. Each computer backs off a different amount, and they make it so that it's fair. So one computer is not always backing the most off, so it's very fair. So it's when you detect a collision, you retransmit after a random backoff. First, you avoid collisions, but in the rare case that you have a collision, then you do this. And so I want to introduce you to the person who invented Ethernet. Ethernet. This is Robert Metcalfe, and he was working at Xerox Palo Alto Research Center, PARC. Everyone calls it PARC. And they were building what is most considered the first computer, the Alto computers. They were connecting line printers, or fast printers to these. Xerox was building the first laser printers, and they needed something faster, and so they just started building it, and they built this thing called Ethernet. Now it's a little different than the Ethernet that we see. The first Ethernet that they built is a little different. You can see a picture of it down here. If you ever go to Xerox PARC and get in, you'll go see this little museum they have. It used a single piece of cable that ran along. They just ran it down the hallway, and they would connect a tap in, and then they would use that to send the data. So they would go down the hallway, and a tap would come out in each office, and they were truly sharing the media. This is not shared except when you plug it into a hub. That's what makes this shared. And it was inspired by an earlier wireless network where they were doing not collision detection but retransmission called Aloha. And a lot of early packet network inspiration comes from the Aloha net come from University of Hawaii. And because they didn't have anything except wireless, but they did have wireless, they did a lot of really cool early research on wireless. And so let's go ahead and meet Bob Metcalfe, one of the inventors of Ethernet.